All right, guys. Two quick lessons today. The two main types of energy we'll be dealing with over the next little while. One's kinetic energy and one's gravitational potential energy. Looks like red's going to work good for this. Yep. So for each of the types of energy, it'll be looking at a quick formula, how to use the formula, kind of common pitfalls, things that can go wrong with it. And then I have a worksheet on each. Best case scenarios, you have a printer, you can just do the work. You can print out the sheets, do the work on the sheet, send me a picture. If you can't print it out, then you'll just have to do the work on paper while you're looking at the questions online and submit that. Either way, that's I'm fine with it. And we'll just go from there. So kinetic energy, it's the energy of motion as discussed in the last lesson. Its symbol is E with a subscript K. Anything moving has kinetic energy. And there are two factors that determine how much kinetic energy you have, mass and velocity. The bigger you are and the faster you are, the more kinetic energy you have. It's wrapped up into this formula, EK equals 1/2 mv squared. M is the mass. It's got to be in kilograms, and V is the velocity, or really we could say speed in this case because the direction actually doesn't matter here. All right, speed. Usually they say velocity, and it's got to be in meters per second. And then EK is the kinetic energy, and it's measured in joules, just like work. Actually, all energies are measured in joules. So let's do a couple of quick calculations. I've got my calculator here, and we're just going to calculate the kinetic energy in each case. The first one's a car, 1,500 kilograms, traveling at 60 kilometers per hour. Well, the first thing I got to do is divide the 60 by 3.6 to get it into meters per second. 60 divided by 3.6 is 16.7 meters per second. All right, and then I just have to go EK equals 1/2 mv squared. So that's going to be 1/2 times 1,500 kilograms times 16.7 meters per second. Don't forget to square that V. And I'm typing it in right now. 0.5 times 1,500 times 16.7 squared equals, well, it's about 21,000. 210,000 rather, joules of energy. Car is very big and it's going very fast. It's got a lot of kinetic energy. Scenario 2, same car, 1,500 kilograms, but now its speed is double. Some people will think that that means that the kinetic energy will be double, but since the speed is squared, it's actually more. Once again, I'll go 120 divided by 3.6 to get my speed in meters per second. I got 33 meters per second. And then I'm going to run the same calculation again. It should actually be 4 times the amount, so it should be about 800,000 because it's doubling the speed, but the speed is squared. So that's 1/2, 1,500 kilograms times 33 meters per second, and that is squared. Let's see if I'm right. Watch, I'm way off, and then we got to start from scratch. I got 820,000 joules. And I am rounding these to 2 digits. My calculator actually says 816750. If you're following along with your calculator, you should get something around that as well. So you can see that doubling the speed actually gives me 4 times roughly the kinetic energy. Scenario 3, I've got the slow car again, but double the mass. Now, doubling the mass is not squared in the formula, so we should get double the base kinetic energy. So I'm expecting around 400,000 joules of energy. I don't need to get the 16.7. I did that the last time, so I'm just going to go EK equals 1/2 times 1,500 kilograms times, what was it, 16.7 meters per second, and that is squared. Put that right down here, 1,500 times 16 point, no, it's not 1500. Guys, you got to jump in and correct me if I make a mistake. The new mass is 3,000 kilograms. So I got to go 0.5 times 3,000 times 16.7 squared equals, and I got about 420,000 joules of kinetic energy. That's a capital J there. So like I said, about double of that base kinetic energy in the first scenario. Now in the last one, we're going to have the heavy car and going twice the speed. So doubling the mass doubles the kinetic energy. Doubling the speed quadruples the kinetic energy. So a double and a quadruple should be 8 times. So this is going to be around 1 million, 1.6 million, something like that. I've got my conversions done already. So all I got to do is go EK equals 1/2 the big mass, 3,000 kilograms, times 33 meters per second. And don't forget to square it if you're following along with your calculator. 0.5 times 3,000 times 33 squared. And I got 1600000. How many zeros? 1, 2, 3, 4, 5. 5 zeros. So 1.6 million joules, or roughly 8 times that original 200,000. That doesn't cover everything I want to with the formula. I'd still like to at least have an example where we have to solve for speed. But that is how the formula basically works. Determine the amount of kinetic energy of a 6 kilogram bowling ball moving at 5 meters per second. Oh, there's a nice easy example to come off of. That's my ugly looking K for EK. 1/2 times the mass, 6.0 kilograms. This will be a lot less because it's not a great big car and it's not moving nearly as fast as a car does. That's why, all things considered, I'd rather get hit by a bowling ball than buy a car. And that gives me 75 joules when I punch that into my calculator. They get a little harder than that. I'm not going to be able to show you that, Mythbusters. I'm sorry. But I wanted to make sure I had one where we have to calculate speed. It's the only time we're going to have to do any significant algebra here. It also gives me the mass in grams. If I divide by that by 1,000 is 0.025 kilograms. All right. Anyway, so I'm gonna write the formula. Now, if you're any good at math, you'll be able to isolate the v before you start. But if you're not that good at math, then you might prefer to write in the numbers first. 0.025 kilograms times v squared. So the next is kind of up to you. Probably the most common thing people like to do next is just multiply the 0.025 by 1/2. So I'll do that now. 0.5 times 0.025, it gives me 0.0125 times v squared. Next, you should divide out the 0.125 on the other side by the 7,800, and I got 624,000. What is this thing, a bullet? Okay, that makes sense. I was going to say this is going to end up going pretty fast. And then the last step, of course, is to square root the 624,000. I'm doing that square root right now, and I got a velocity of, I'm going to round it to 790 meters per second, which is about twice the speed of sound, and that's pretty good accuracy for what the speed of a bullet should be. You could ignore that homework. I'm just getting you to do the worksheets that go with this. I'm going to keep those annotations, and I'm going to open up the other lesson. So that's one of the two calculations I want to show you how to do today. The other one is on gravitational potential energy. And gravitational potential energy is stored energy. We learned about that in the last lesson when we were talking about types of energy. And gravitational means it's got to be raised up above in some sort of gravitational field, in our case above the Earth. It's the energy stored in an object due to its position above the Earth. It takes work, force times distance, to lift an object up, and that work is stored as energy in the object. We kind of did gravitational potential energy with that flag being lifted up. Oh, and the work done to go up the stairs, it's the same idea as well. How much work does it take to lift 3 kilograms, 2 meters off the ground? Remember, work equals force distance. The force here is the force of gravity. So it's 3 kilograms, 9.81, and then times the distance, which in this case is 2 meters. That's essentially calculating the gravitational potential right there. 3 times 9.81 times 2, and it gives me, I'm rounding that to 59 joules. That's a way that you can do that. When you're lifting something up, you always are lifting with the force of gravity. So you can put that in and make just one equation, which apparently I'm going to have to write out. So instead of work equals force times distance, it's going to be, when you're lifting something up, gravitational energy is equal to the force of gravity times distance, or height. So I'm going to write an mg, since that's the force of gravity. Instead of d, we know we're always raising it up, so we change the d to an h for height. That is the formula for gravitational potential energy right there. All right, so that's the note. Now just some examples on how to use it. A car, 2,250 kilogram car, 4.8 meters above the ground. What's the gravitational potential energy? Should be a piece of cake. Eg equals mgh, which is 2250 kilograms, 9.81 times 4.8 meters. If anything, this is easier than the other calculation because nothing's squared, so you're never going to forget about squaring that thing. So I got about 11000. 1, 2, 3, 4, 5. Yeah. And again, that is rounded. That's not exactly what it said on my calculator. I rounded it to 2 significant digits. As always, I'm going pretty fast here. Pause the video when you need to catch up. Good. We've got one like this. So it took that much energy to lift this object. What was its mass? So just an example where we have to solve for mass. It gives me the gravitational energy. Now notice it said, oh no, it did say energy. Sometimes what it'll do is it'll substitute in work. It means exactly the same thing. If it took that much work to lift it, that's also the amount of gravitational energy. Work and energy can be used interchangeably in this unit. So just be aware of that. 9.81 and then a height of 5.6 meters. I'm going to multiply this times this, and then I'm going to divide it over under the 87,500. Might even actually do it in one swoop here. 9.81, 5.6, and I got a mass of 1,600 kilograms. That is rounded. I got 1592 on my calculator. So that's about as hard as that formula really can get. I guess that's one of the only ones we're going to do. So there's nothing, there's no curveballs on the two worksheets. If there is, and I'm just mistaken, feel free to send me an email. You can privately comment to me in that section. But I think there's a lot more number crunching to do here because you got to use this formula over and over. But there's much less confusion. You don't have to worry about the zero work situations or anything like that. So you should have an easy time with it. And if you've already done the Monday, Tuesday work, this is all I'm leaving you with for the rest of the week. Get the stuff from Monday turned in, get these two worksheets turned in, and then forget about physics, hopefully, for the weekend. All right. And make sure you sign the attendance. This will be the last official post I do this week. Maybe I'll throw out a reminder on Friday to get all your work in and to sign the attendance form, but do that. We got an email yesterday saying to submit names of students who aren't connecting. So I just go by those attendance forms to see who's on and who's not on. All right, guys, I think that will be all for now. If I can find the exit button, here it is. Okay, good luck.